Okay, well, just 1 minute left, so I am glad to introduce you our today's speaker. It is Eivind Schneider, and the talk is a joint talk with Boris Krupnikov. Eivind, you are welcome to begin.
Thanks a lot. So let me start with expressing my gratitude for the opportunity to speak here, and thanks all of you who are coming to watch. I would like to talk about a recent project that I've been working on together with Boris, and it's about invariant divisors and equivariant line bundles. And so this talk is based on an archive preprint with the same name. So just pick some of the results, and hopefully you'll find some of it interesting. The setting that we will be having for the rest of the talk, more or less, is that we assume you have a Lie algebra G of holomorphic vector fields on a complex manifold M. And then one of the natural questions that you can ask is, what are the G invariant submanifolds? Our motivation was originally to compute invariant differential equations, so of course submanifolds inside Dutch spaces. And we'll come back to this towards the end. But for now, we'll just try to consider the general picture here. This is a little bit too ambitious for now, so we'll consider the simpler question. Try to answer what are the G-invariant hypersurfaces, codimension 1 varieties, subvarieties. Right, so the contents of this talk is basically the following. I will start by talking about relative invariants and their weights, and then about divisors and line bundles. The first 2 points are things that are well known, and there are some interesting interpretations of these things in terms of different cohomology theories. But after that, I will mix these 2 points together into invariant divisors and equivariant line bundles, which kind of gives us a way to answer the bold-faced question above. And also here you will get a cohomology theory, basically by mixing these two types of cohomology. So you get sort of a complex, you get a double complex, and we'll see how this works later. And in the end, I will talk about applications to Dutch spaces, which was our original motivation. Right. So let us just start with a simple example. And now I will be working over R, just because it's easier to draw pictures there. But this is the only slide where I'll do that. So we have our two-dimensional manifold. We have a one-dimensional Lie algebra vector fields on it, and you can see that this corresponds to that Lie group action here, if you prefer to think in terms of Lie group actions. And the orbit structure is quite simple. You can very easily see what it is. So here I drew some orbits. So the red one, for example, is one orbit. Blue one is one orbit, and so on. But we do have some special orbits, namely the x-axis excluding 0, and the y-axis excluding 0. And 0 itself is another special orbit. So if you wanted to describe hypersurfaces here, assuming that the problem was not this simple, how would you do it? A natural approach is to start with finding the absolute invariants. These are functions that are constant in orbits. In this case, there is only one generator for this. And the way you find invariant hypersurfaces is just to take the level sets of this absolute invariant. To find this, one way to do it is to try to solve this linear PDE system. Well, now it's just a PDE in general. If you have several generators of the Lie algebra, it's a system. And these absolute invariants are reasonably well understood in different settings. the local smooth setting, you know that by the Frobenius theorem that the number of independent absolute invariants is equal to the codimensional a generic orbit. And in the global algebraic setting, Rosenlicht's theorem tells you that generic orbits are separated by rational invariants, and the field of rational invariants has transcendence degree equal to the codimension. Right, but in general, the absolute invariants do not give all hypersurfaces. We see it here in particular. We're not able to pick out the coordinate axis completely. Okay, we can get, if c is equal to 0, we get their union, but we would like to get each of them separately. And also, that picture may be quite different than this. And it is important in general to pick out the other hypersurfaces. And in this case, I already explained what they should be. There are two functions, x and y, and they are relative invariants. So for relative invariants, their zero sets are invariant hypersurfaces, while for absolute invariants, general level sets were invariant hypersurfaces. So to get these special hypersurfaces, we need relative invariants. In general, they are solutions to a system of this type, where, well, before we had 0 here, now we have something proportional to r, and this lambda depends linearly on x. In this case, lambda x is plus or minus 1 for these two relative invariants. But this is not, in general, PDE system we can just solve because, well, first of all, we don't know what lambda should be. And also here, there exists some results in the local smooth setting, but I'm not aware of any of many like global results similar to what I will talk about today. So the goal here is basically to get an understanding of globally what these relative invariants should be. So that's the simple picture. So let me just give a proper definition of relative invariant. So a relative invariant is, with respect to some algebra of vector fields, is a function. Now we're in the complex category, so we consider holomorphic functions satisfying this system here, where now lambda is a function valued one form on the Lie algebra, which we will call the weight of f. So one question you can ask is what are the properties of lambda? Can it be just any element here? And it turns out no, it cannot be. So because we put, for example, this condition, if you apply the commutator of two vector fields in the Lie algebra to f, on the one hand, by definition, you should get this result. On the other hand, if you expand and simplify, you get this result here. So that gives a condition on the lambda, namely that this expression should be 0 for every pair x and y in G. So I'll give this a name, call it T1 of lambda applied to x and y. Furthermore, if we adjust our relative invariant with some non-vanishing function, here, so the exponential of some function, then it doesn't change the 0 sets of f. So in this sense, the invariant should be considered as equivalent. And if you apply an element from a Lie algebra to this, use a product rule, and you see that the weight is changed by x applied to mu. So it means that the difference between weights of two equivalent relative invariants is basically this, and we'll also give this name d0 mu applied to x. And these d1 and d0 may look familiar to many of you because they are differentials in the Chevalley-Eilenberg complex of G with coefficients in the G module of holomorphic functions on M. So I have this picture here. So by the previous slide, weights of relative invariants are basically elements inside this Chevalley-Eilenberg cohomology group. We should make a small modification because in general, it's not the case that any non-vanishing function is exponential of a function. So let's instead, in general, consider a non-vanishing function. The cross signifies then doing the same computation, we see that the weight will change by this. So we'll make this modification to the Chevalley-Eilenberg complex. Instead of O, we have O cross, and instead of D0, we have D0 log. And then we consider the cohomology here. So I'll just show with a very simple example how this can be computed. And I'll use the notation A for lambda of x, B for lambda applied to y, and then lambda is just a general representative of the cohomology group. So let's see what we get. Well, we are allowed to modify lambda with a coboundary. And by doing so, we see that we get this expression. And by choosing mu appropriately, it's not difficult to see that we can remove almost all of A. Basically, we can set it equal to a constant. When we have done that, we can look at the co-cycle condition. That's this. Well, x, the commutator of x and y is just y, and lambda of y is by definition b. We also see that y applied to A is 0 because A is constant now. So we get this very simple ODE, easy to solve, and we get this solution here. So it's, it's given in terms of another constant. So we have two constants that parameterize the lambdas. So the result is that this Chevalley-Eilenberg cohomology is two-dimensional. On the other hand, it's not difficult to see what the relative invariant in this case should be. So because there are only two orbits here, it's 0 and its complement. So 0 is the singular orbit, and so x is fundamentally relative invariant, and we can take it to any power. If you want it to be holomorphic or meromorphic, we need to make A1 positive integer or just an integer. So we see that only a small portion of the weights here are realized by relative invariance. Yeah, because this relative invariant, it has weight basically given by A1. Now A1 is an integer, and also A2 has to be equal to A1. So yeah, we will very soon come back to this question about realizability of weights. First, we need to talk about lifts of G to this trivial line bundle. So if we want to lift G to this line bundle, what we do is basically choose a coordinate on the fiber, and then we add this vertical term where lambda x depends on x, but it's a function on m. And you see, I use the same notation for lambda as before, and the reason is that they are very closely related, as we will see soon. In particular, if we require this lifting procedure to preserve the Lie bracket, which we obviously should, then it implies that lambda is in the kernel of the differential over. Yeah, it's a co-cycle in the Chevalley-Eilenberg complex. Moreover, if we change the fiber coordinates, because we can do that, multiply it by some non-vanishing function, then we will change from lambda to this tilde lambda, and the difference is this term here, which is a co-boundary in the modified Chevalier Island complex. So we see that the lifts here can be identified with this cohomology group. And we also notice that F is a relative invariant with weight lambda, and G hat lambda is the corresponding lift to C, so that it's given by the weight. Then this section here is actually a G lambda invariant section on of the trivial bundle. So now we're ready to talk about realizability in a little bit more detail, and we'll find some necessary condition for a weight to be realized by some relative invariant. And this is basically taken from Mulver, 1997 paper. They did a lot more, but we'll simply pick out a nice little argument from there. This goes like this. So we take the given weight or the element inside of this cohomology group, take a representative, compute the lift like before, and F is a relative invariant. Then, of course, it satisfies this by definition for every x in G. And if you now apply the lifted vector field x hat to this ratio you divided by F, then simple computation with a quotient rule, it shows that you actually get 0 here, since, well, if you apply x hat to u, of course you get lambda x times u, and if you apply x to or x hat to f, it's the same as x applied to f, and that again gives lambda. So they cancel out and you get 0. So you see that u divided by f is an absolute invariant, and it's an absolute invariant that comes in addition to pullbacks of the absolute invariance on the base on M. So that means that the orbit dimension, when you lift, it remains the same if such a relative invariant exists. So in particular, if there exists a relative invariant F with weight lambda, then the dimension of generic G orbits on M is equal to the dimension of generic G hat lambda orbits on the trivial bundle. So this is a necessary condition. It's not sufficient in general. In some cases, for example, if G is coming from an algebraic Lie group, we showed that there is something very close to a converse of this statement, but in general, it's not true. All right. So let's now talk a little bit about line bundles. Probably this is well known for most of you, but at least we'll set some notation. So any holomorphic line bundle is locally trivial. So there exists a cover that trivializes it. And this line bundle is uniquely defined through its holomorphic transition functions. And there is an interpretation of this in terms of cohomology again. So here is the check complex over the fixed cover U. And the transition functions, they are required to satisfy this co-cycle condition. So they go to 1 here, basically. And then there is also a freedom in choice of transition functions, and that corresponds exactly to a co-boundary here. Yeah, so this collection of transition functions, it represents an element of this cohomology group over the fixed cover. And in general, we should take the direct limit of this as the cover becomes finer and finer, and we got proper check cohomology. And this is in general isomorphic as a group with the group of line bundles, and the group operation on the line bundles is the tensor product. And we call the group of line bundles the Picard group. Right, so then there is one more concept that we need to discuss, and it's that of divisors on M. And it's a fact that any holomorphic hypersurface in M can be defined locally as the zeros of a holomorphic function. And a divisor captures this on a global level. So divisor is a global section of the quotient sheaf. So here we have the sheaf of non-zero meromorphic functions, modulo non-vanishing holomorphic functions. And yeah, any divisor can be given on some open cover as a collection of meromorphic functions. So one function defined on each open chart. They are required to be consistent in the sense that they share zeros and poles. So if you take their ratios, they should be non-vanishing holomorphic functions on overlapping regions. And also, if you define a divisor like this, the representative is usually it's defined only up to a factor of non-vanishing holomorphic functions. So there is some freedom here in how you write it down, the representatives. And whenever you have a divisor, you can construct a line bundle. So we have a map from divisors to line bundles, and it goes like this. If you have written your divisor in terms of representative functions, then the line bundle bracket D is defined by transition functions of this type. So you just take ratios of the defining functions. And of course, they are required to be inside of here, so which is where G alpha beta lives. And also, it's not difficult to show that they satisfy the cocycle condition. And it's also well defined under change of representative. You can also quite easily see that the divisor defined in this way, it also defines a meromorphic section of this bundle given in this way. So the idea is the following. We will, so G invariant hypersurfaces, it should be given by G invariant divisors or equivalently sections of G equivariant line bundles. That's our reason to study these divisors and line bundles. Okay, so let us talk about G equivariant line bundles. In the context of groups, these have received much more attention. There are many papers written about it, but in terms of a Lie algebra, I haven't seen, I don't know about any papers devoted specifically to this. And it's actually slightly different. So let G be a Lie algebra vector field on M. We define a G equivariant line bundle over M to be a pair of a line bundle L over M and a lift G hat to the total space. Lift in the sense that I showed on my previous slide. So what do we get from this? Well, locally, we know that line bundles are trivial, so we can choose trivializing cover. And in these local charts, where we have the trivial bundles, then we can do the lift that we did on the previous slide. We just label it by alpha. And we have the following data. So we have a collection of local lifts. We know that they have to satisfy, they are so cocycles in the Chevalier-Eilenberg complex. And we also have transition functions for the line bundle L, and they are cocycles, or the collection is a cocycle in the Chevalier now in the check complex. But there is one more thing we should make sure, namely that these lifts are compatible. So what does that mean? Well, if you consider overlapping regions, so I use this notation here as a shorthand for the intersection between two sets. We need lifts to be the same. Okay, of course, to compare them, we should choose the same fiber coordinates. So to convert from the alpha, to the alpha, from alpha to beta, we use the transition functions. And we see that this is equal to this expression here. And this can't readily be compared to this. They should be equal. And we have this compatibility condition that holds on the overlapping regions. Okay, so let's try to understand this. So we already stated that the G-equivariant line bundle is given by a pair G lambda. Lambda satisfies this co-cycle condition, G satisfies this. And here I've drawn up the Chevalier-Eilenberg complex horizontally, the check complex vertically here, and our lambda lives here, G lives here. And then I have written the compatibility condition like this. And what do I mean by this? Well, basically, we can extend this to a double complex. So we have also a delta 0 here and d0 log here. And we require that, so when we have a pair, the compatibility condition says that whatever is here should go to the same as what's here. It should go to the same element here. Right, so that's these conditions. So that we see some kind of diagonal pattern here, which suggests that this can be formulated in terms of the total complex of this double complex. So to do this, we just unify notation a little bit, and we'll call this C00. This is C10, C10. This is C01, C11, and so on. We'll also make a unify the notation for the differentials, and we'll get this. This is the same picture, just in different notation. Right. So we'll make the total complex like this. So tot 0 will just be C00. Tot 1 will be the product of the blue elements here. Tot 2 will be the product of these three elements, and so on. And we also have a differential defined like this. Basically, the square of this equal to 0 is equivalent to commutativity of this diagram. And these conditions are exactly that this del1 applied to the element here goes to 0. All right, so from above, the conclusion is that the line bundle is given by a del1 cocycle in the total complex. And if you modify this pair with a co-boundary in the total complex, get this. It's a little bit confusing because you have a mix of multiplicative and additive notation. That's just how it is. So it turns out that this change corresponds exactly to the freedom we have in the fiber coordinate. We already saw that if we change the fiber coordinate like this, the lambda is changed like this. But it's not. It's also not difficult to see that. The G changes in this way because change to tilde u alpha, then you convert from u alpha to u beta using the transition functions. Then you want tilde u beta, and then you have to divide by u beta, and you get basically G alpha beta multiplied by this co-boundary in the check complex. Yes. So if we denote the group of G equivariant line bundles by pick Gm, you see that if, at least if the cover is sufficiently nice, then pick GM is isomorphic as a group to H1. So the first cohomology of the total complex, or more generally, you can take the direct limit of this as the cover becomes finer and finer. And recall that the double complex C was defined in terms of some open cover. So you can refine it and take the limit. And then they are isomorphic. And this actually has a name, often written like this. So it's called the first hypercohomology of the Chevalley-Eilenberg sheaf complex. Hypercohomology is then a general notion for sheaf complexes. So let's look at a slightly more difficult example than the previous one, but only slightly. We still have a one-dimensional manifold, so now it's CP1. Still have a two-dimensional Lie algebra. We cover CP1 with two charts. So the standard coordinates, they are related in this way, y and x. In the U0 chart, the vector fields are given this way. And in the U infinity chart, they are given this way. We see that actually this is the same vector fields that we considered in the previous example. So the previous example was a local version of this. And we already computed this Chevalley-Eilenberg cohomology coefficients in this G module of holomorphic functions U0, just given like this. And then completely similar computation gives us slightly simpler result on the other chart because we get only one parameter here. Then we need to check compatibility. That's, since we have a two-dimensional Lie algebra, that's two equations, this one for x and this one for y. Just rewrite them, and we see that we get this ODE and this ODE. It's almost exactly the same ODE if you divide by x. Only problem is that the coefficients in front on the left-hand side are different. So we need them to be equal for this system to be consistent, implying that B1 is equal to A1 minus A2. And then we solve and we get the general solution x to the power A2. And looking for holomorphic transition functions, we require A2 to be an integer. So in other words, yeah, we have two parameters. We have one integer parameter and one complex parameter. So pick GM, the group of equivariant line bundles is C times Z. So last definition for today is that of a divisor. A G-invariant divisor, in fact. So a divisor given in terms of these local functions and some cover is G-invariant if there exists an element lambda now in this C10 in the total complex, such that for each in the double complex, such that for each alpha these equations hold for any x in G. And it turns out in the same way as that any divisor gives rise to a line bundle, turns out that any G-invariant divisors gives rise to a G-equivariant line bundle. And it occurs in this way. So let G be a Lie algebra vector fields on M. Let D, given by F alpha, be a G-invariant divisor with weight lambda. Then the pair G lambda, where G is defined this way, the pair defines a G-equivariant line bundle. Right, and of course the lift is then given by lambda. And we get them up from divisors from G-invariant divisors to G-equivariant line bundles. And in some case, yeah, this is important because you can imagine that this it gives a bound on what the possible weights of G-invariant divisors are. But I should also mention that this map in general is neither injective nor surjective. The kernel contains, for example, all globally defined absolute invariants. Every globally defined absolute invariance goes to 0 here. It's also not subjective, which we see in our example. So let's just continue this example. This is from the previous slide, same computations, we ended up with this transition function. And these lifts, so now B1 is equal to A1 minus A2. So let's consider the lift on the infinity chart. To get this, and we remember the necessary condition for a relative invariant with this weight to exist is that the dimension of orbits of this lift is the same as dimension of orbits of the original Lie algebra, which was 1. So if the dimensions of these orbits are, if generic orbits have dimension 1, then A1 has to be equal to A2. So we get A1 equal to A2. And then solving for solving the equations for the invariant divisors with these weights, we get this expression here. So F0 and F infinity is the defining functions for the divisor. Here we see that in this case, A2 has to be equal to A1, and they both need actually to be integers for this to be a meromorphic divisor. And we also notice, again, that in general they are not the same. So the divisors, the G-invariant divisors, are just set, while G-equivariant Picard group is C times set. In particular, the map is not surjective. Right, so let's go to curves in the projective plane. And we'll consider differential invariants, basically invariant divisors in jet spaces. So, right. So if we're doing computations here, we need to choose an open chart of CP2, choose the standard one, homogeneous coordinate set, assume that W is non-zero, and then divide by W, and we get 2 coordinates. In order to get coordinates on the jet bundles, we need to choose an independent variable and a dependent variable. So we choose Y as a dependent variable. And this gives the coordinates chart here. So we have coordinates X, Y, and Y1, and it covers a part of J1. So the basis of SL3 prolonged to J1 can be given like this. We have 8 vector fields. And now we can do the same type of computations that I did earlier with the simpler example. Basically, we take a general representative here, and use a co-boundary to set this equal to 0, and this equal to 0, and also this equal to 0. And then the remaining co-cycle conditions will give us the remaining functions here. And we see that there are 2 constants appearing, A1 and A2. So this local Chevalier-Eilberg homology It's just C2. But of course, we have to also compute in the other charts. So let's keep the same chart on CP2, but now we change the dependent variable to x. Okay, that gives a slightly different chart of J1, and we have coordinates x, y, and x1. And of course, x and y are related to the previous coordinates in the obvious way, and x1 is 1 divided by y1. And now we get this basis. And expressions are the same, but they are shuffled around a bit. And again, the computations for lambda is also the same, only that instead of the fourth, setting the fourth to 0, we'll set the third to 0. And that's because actually the third and fourth vector fields here, they kind of change roles when we change role of x and y. Computations are exactly the same, and we'll get 2 parameters again, which I now call B1 and B2. And then we should also, so we get the same thing here, but we should also check compatibility. And going through this, we will see that compatibility condition leads to A1 equal to B1, A2 equal to B2, and then we get this general transition function. And for this to be holomorphic, we require A1 to be an integer. So we went from C2 to now C times Z, but we still have more charts. So to cover CP2, we need 2 additional charts. These are the standard ones. So if we do the same computations for these charts, again, requiring analyticity of the transition functions. So for example, we take U2, we pick y as dependent variable to get coordinates on J1. We look what happens on the overlapping region here. And then analyticity of the transition function would lead to this condition here. So we lose some more freedom. So basically, these line bundles are parameterized by 2 integers. And in this case, the situation is quite easy to understand. We have simple manifolds that we are working with. So if we let omega denote the contact form on J1, then omega spans inside of the cotangent space of J1, it spans a line bundle. So we get 1 line bundle from that. Now also, we have the tautological line bundle over CP2, which is often denoted like this. And they together generate the G-equivariant line bundles. So we have this result here that the SO3 equivariant Picard group on J1, it is generated by these 2 line bundles. Of course, we need to take the pullback of the line bundles of CP2 to J1. And then the relation between the parameters A and K is this here. So let us look a little bit closer on this. Consider some relative invariants, and this is well known. I think it was first computed by Halfen almost 150 years ago, and there is more recent nice treatment of this by Konovenko and Lyshagin. So on J2, there's basically 1 relative invariant. On J5, there is 1 additional relative invariant. And on J7, we reached a point where the dimension of the space is larger than the Lie algebra. So we actually get an absolute invariant, but in particular, we have this relative invariant, and a certain combination of these will be a rational absolute invariant. So let's try to see what kind of weights or line bundles that we can get from these. Well, first of all, yeah, so here on the left-hand side, I've drawn the gray dots. They are basically the G-equivariant line bundles. See that I have K0 and K1 on the coordinate axis. So the gray dots are the possible line bundles. And you can see just by looking at the weight of R2 that it corresponds to this line bundle here. The other two, they will be far outside of this picture, but you can take some combinations. For example, R5 divided by R2 to the power 4. You get the line bundle here. And then making this combination, you will get this line bundle here. And in particular from these two, basically you can get all the blue dots by taking suitable combinations. In particular, you can you can combine these three also to get an absolute invariant here, which corresponds to the trivial bundle. So there are two things we notice here. And well, we see them only for this very small set of relative invariants, but it's actually general. So first, only this subset of line bundles are realized by rational relative invariants. Okay. Right, at least we see it from J7, but it's not clear if it also works for higher order, but it actually does. And to explain this, we should look at, so I've been only talking about the Lie algebra, but there is actually a Lie group also somewhere behind here. And when you talk about the SL3 Lie algebra, there are at least two natural groups that come to mind. It's the group SL3 and it's the group PGL3. And the group lying behind here is PGL3. And there exists no lift of PGL3 to the tautological line bundle. But it does exist a lift to its, what is it? Third power, which is basically the canonical bundle. So the top exterior product of the cotangent bundle. So that's why we only get these blue dots realized. There is also one other picture, or another thing that's important to notice, and that's that the weights here depend only on J1. So even though we have invariants over 7, they actually corresponds to line bundles over J1, which may be surprising. So in the last couple of minutes, I will try to explain this phenomenon, because it's actually a general result. So let's talk about polynomial invariant divisors on jet spaces. So we will consider jets of submanifolds of some manifold E of codimension M. And we then call divisor polynomial divisor if its restriction to fibers of JK to J1 is polynomial. So when I say the divisor is polynomial, I mean the representative functions f alpha. And this notion is independent of the choice of coordinates on E. And that's actually also why we go to J1 here. We cannot, in general, go to J0. Then we have the following statement. So if G is a Lie algebra of point vector fields on J0, and D are GK invariant polynomial divisor on JK, then the corresponding line bundle is actually the pullback of a G1 equivariant line bundle over J1. And that explains basically the last point of the previous slide. So I'll try to outline the argument for this quite briefly. So let T be a polynomial divisor on JK, defined on the open cover here. So we assume that we have some open cover on J1, and then the fiber over each of these charts will give an open cover on JK, like this. And then we take the transition functions, f alpha and f beta, take the ratio, and we get something here by definition of divisor. Now, these f alpha and f beta, they're polynomial in the jet variables of order 2 and higher. And for them to, first of all, well, be non-vanishing and also have no poles, polynomial parts have to cancel out. So they actually drop, this ratio drops to a function on u alpha intersected with u beta, just on J1. So that's the first part. This was the part of this statement that involves the line bundle, but we also have another part. We need to talk about the lift or the weights, lambdas, so that they depend on J1 only. And to do this, I would like to take a look at this simple prolonged vector field. So this was one of the elements in the SO3 realizations that we have been working with. So we prolong it to J4 and want to introduce the weighted degree here. So again, we only care about, well, we have a polynomial in second order variables and higher. So y1 is not considered here. So we'll basically look at the degree here, but we will give the higher order variables more weight. So here you can say that this is weighted degree 2 because there is y2. Here we have one term of weighted degree 3. Again, we don't count y1. And here we have the square of something of weighted degree 2, so it's weighted degree 4. So this in totality has weighted degree 4. Similarly, here you have 2 and 3, that gives 5, weighted degree 5. So now if you imagine that you have a relative invariant, a polynomial relative invariant, you apply, for example, this last term to the polynomial invariant, then this will reduce the weighted degree by 4, but then we have afterwards to add something weighted degree less than or equal to 5, right? And this picture is general. I show only a simple example here, but in general, these terms kills. So it subtracts something of weighted degree k, and this adds something of weighted degree less than or equal to k plus 1. So if f alpha has weighted degree d, then xk applied to f alpha has weighted degree less than or equal to d plus 1 for any x in g. And since we have this relation here, so yeah, weighted degree d plus 1, weighted degree d, it follows that lambda alpha has weighted degree less than or equal to 1. Therefore, it cannot depend on variables of order 2 and higher. So it's actually a function on J. Right. So why is this important? Well, it means that, well, in general, if we're interested in invariant divisors here, we could start by trying to compute G equivariant line bundles over JK. But then it would mean that we may have to go to arbitrarily high order K and do the computations again and again. But it turns out that if you look for polynomial invariant divisors, and actually by extension irrational invariant divisors, then it's sufficient to compute equivariant line bundles only on J1. I should also say that we can modify this statement in different settings. I won't write it down in detail, but for example, if E is a total space of a fiber bundle, and G preserves fibers, then we can consider polynomial divisors that are actually polynomial here on the fibers jk over j0, and then we have a similar result, but we need to consider only line bundles over j0 instead of j1. And then you can also consider in special cases consider contact transformations instead. And then you have to go up in order. Right. So yeah, I think this is a natural place to stop. So let me do that, and thank you all for your attention. Thank you.
Thank you, Eivind. It's very interesting questions, remarks, comments. Well, I have a question. Can anything reasonable be said in the real valued case, not in the complex?
Right, that's a good question. So we started with this complex case because the theory of divisors and line bundles is very
of course,
well developed there. So if you do these computations, let's say, for example, this over the reals, as far as I can see, the computations look the same. There are not big differences here, at least if you consider, well, it's also a question of analytic versus smooth. So in particular, here, to get this huge constraint on A1, but it is an integer, we actually need analyticity here. If it's smooth, then I'm not completely sure what happens. Yeah.
More questions? Well, thank you very much again, and thank you for agreeing to deliver a talk here. And I hope it is not your last talk in Australia. So you are always welcome. So thank you very much. Goodbye, and we'll meet in a week.
Thanks.
Bye-bye.